All right, so hi everyone, welcome to this week's IRIS-HEP topical meeting where we're going to have two student presentations on different topics. So our first one is going to be from Irina. So Irina, if you want to go ahead and share your screen, that would be great.
Sure.
Perfect. So why don't you go ahead?
Okay. Hello, everybody. My name is Irina, and I'm a grad student at UC Berkeley in the physics department. And today I would like to tell you about the work that I have been doing over the past summer with the ACTS group at UC Berkeley on trying to use machine learning to ambiguity resolve reconstructed tracks within ACTS. So I'll start with a few introductory and motivation slides about tracking, ambiguity resolution, and ACTS in general, and then I'll talk about the details of my project, in particular about how we trained a neural network to perform ambiguity resolutions and some of the lessons we've learned, and then how we try to implement this predictive functionality back into ACTS, as well as make a few comments on future directions for this project. So, at the high luminosity LHC, we expect to see an increase of almost 2 orders of magnitude in the number of reconstructed tracks compared to, for example, LHC run 1. The greatly increased combinatorics that will result from this will certainly stress the available computational resources, which means that it's going to be necessary to have fast, accurate, and efficient track reconstruction algorithms if we want to achieve our relevant physics goals. And an example of this type of algorithm is the work being done for the ACTS project, which stands for the ACTS Common Tracking Software, or a Common Tracking Software, depending on which particular type of acronym you like. And the ACTS project wants to be a track reconstruction toolkit that is inspired by the experience from Atlas, but that is nonetheless experiment independent. And it also aims to be a platform for the implementation of novel tracking techniques, as well as new hardware architectures. The ACTS project aims to fulfill the fast, accurate, and efficient requirement by adopting a code implementation that is based in a modern version of C++, with great care taken towards efficient memory allocation, thread safety, providing rigorous unit testing for all of the code functionality, and also for the user side, providing good documentation, amongst several other things. But one other thing that we have to keep in mind is that the performance of tracking algorithms is not quite 100% across the board, which means that not all reconstructed tracks are going to be real tracks that belong to actual particles from which we can gain useful physics insight. So in the particular case of Atlas as well as ACTS, this is why we need an extra step, which is called ambiguity resolution. And this is going to help us pick the good, true tracks from a set of possible track candidates that the algorithm provides. So to provide a little bit more context into what ambiguity resolution does, let me very briefly explain the track reconstruction chain that is used in Atlas. So the first step is the space point formation step, which finds the location of the particle hits in the various layers in the detector. Once these are found, the next step is called the seed finding step, and this consists of finding compatible groups of hits and using them as seeds for the initial starting point of a possible track. Then each seed is extended to find more relevant hits in other parts of the detector during the track finding step. And here, this extension is done using a combinatorial Kalman filter, which will mean that all possible and realistic combination of hits are going to be considered. Because we consider all possible combination of hits, this is going to end up generating at the end a set of track candidates. And among these candidates, not all of them are going to correspond to the true real track, but we will also have some candidates where we will have overlapping hits or perhaps incorrectly assigned hits. So this is why at this point we need ambiguity solving, because this is going to allow us to separate the good true tracks from the other tracks, which are sometimes called duplicate tracks, the one that have overlapping or shared hits, and the ones with mostly incorrectly assigned hits are the fake tracks. And then the final step is extending the track even further in other parts of the detector. So in Atlas, the actual ambiguity resolution decision is done by scoring the track candidates using a simple function. And this function is based on certain track quality features. So for example, if a track candidate has a lot of hits, this is going to increase its score. If it has a lot of holes, this will decrease its score, and so on. So each of the possible track candidates get a particular score, and the one that has the best score is picked as the best candidate from that set, and so on. In ACTS, what we currently have is a type of performance validation, which very loosely does a type of ambiguity resolution in the sense that we have information about the true particles that we get from the simulation, and then we can use this truth information to label the tracks as being either a good or a true track, or a fake track, or a duplicate track using the certain truth-based information. But another possible way in which we want to do ambiguity resolution could consist of using machine learning. And in particular, because we have this truth information available to us, we can use a neural network and train it based on this truth information to recognize whenever a certain track that it's being presented with is either a good track, a duplicate track, or a fake track, based on some set of features that describe that particular track. And here I'd like to add a disclaimer, which is the fact that the track information that we have currently and readily available to us to use for training is still at the rather simple stage. So this will certainly limit the extent of what we can actually do with our network. So the first step in trying to train our network is to generate a training data set. And here we use the fast simulation in ACTS, and we use it to generate simulated particles and hits. We generate 50 TT-bar events at an average pileup of 200 inside of a generic track ML-like detector, and also in a constant 2 Tesla magnetic field. Then once we have the simulated hits, we can use a combinatorial Kalman filter to find the tracks and also fit the tracks. And again, because we have access to the truth information, we can assign a label of either a good track, which corresponds to a track in which almost all of the hits belong to one true particle, or we can assign it to be a duplicate track. This is the case where the track shares some of its hits with an already identified good track, or we can even have fake track, which corresponds to the case in which almost all of the hits are actually incorrectly assigned to this particular track. So once we do this, we find that in our data set of around 115,000 reconstructed track candidates, about 86% correspond to what we would call good tracks, and the remaining 14% or so correspond to duplicate tracks. What we found is that our fake rate is actually quite small. It's less than about 0.01%. So what this means is we don't have enough fake tracks to be able to train a good network. So we just decided to not use the fake tracks at all, and instead focus on doing a binary classification in which we train the network to distinguish a track as being either a good track or a duplicate track. As mentioned before, the set of available features is simple, and it corresponds to, it consists of the number of hits that a track has, the number of outliers per track, the number of holes per track, and also the chi-squared per degree of freedom of the fit to that particular track. However, I'll note here that the more interesting part will come once we have a more realistic detector description available. And here I'll comment that progress is actually being made in that regard, as just last week, the ITK geometry was first integrated into ACTS. If we take a look at the distribution of our training features among our track candidates, we can see that there's some separation in the distribution for good tracks versus duplicate tracks, in the sense that on average, we can look and see that the duplicate tracks tend to have fewer hits and more outliers than the good tracks. However, we also notice that there is some significant overlap between the distributions for these two features, and this will likely complicate things further down the road. The same conclusion also happens for the distribution of the chi-square. Again, duplicate tracks tend to have a higher chi-square than good tracks, but there is also non-negligible overlap between the two distributions. What we found for the holes was that since our detector description does not consider any inefficiency in the modules, almost all of the tracks end up having no holes, regardless of whether they were labeled as a good track or a duplicate track. So this means that the whole information is actually not informative for us. So we just decided to not use it because it wouldn't contribute any useful information. So once we have a training set, we can proceed to build our neural network. And we do this by using TensorFlow, and inside of the TensorFlow framework, we construct a deep neural network. The architecture for a particular network model is shown in this graph, and it consists of an input layer, which stores the information about our training features, which is fully connected to one hidden layer that has 3 units and a ReLU activation function. And this is, again, fully connected to one output layer that has 1 unit and a sigmoid activation function, which is appropriate for the particular classification problem we're looking at. So what the network is actually going to output at the end, after being shown a particular set of features, is going to be the confidence level that the network has that the particular input it was shown corresponds to a duplicate track. Some additional features that we used were the binary cross entropy loss, which again is appropriate for this problem, and also the Adam optimizer with the default settings. But again, keep in mind that this set of features is simple, so this will certainly limit how fancy we can get in terms of the architecture that we can use for our network. Of course, the end goal is to eventually, at some point in the future, develop a more complex architecture, but this will require moving beyond the current set of features that we have available. So with our network in place, we can begin to train it, and we follow the usual machine learning recommendations in this regard. We split our data set into a training set, which consists of 75% of the data, and then a test set, which consists of 25% of the data. And we're going to use this to assess our network's performance. So we expose our training data to the network, and we ask it to find the optimal weights such that it maximizes the area under the curve of the receiver operating characteristic, which is shown for our best model in the plot on the right. And our best model turns out to have an area under the curve of 0.87. And for comparison, a purely random model would have an area under the curve of 0.5, and a perfect model, which gets every single prediction correct 100% of the time, would have an area under the curve of 1. And remembering now that the actual raw output of our model is that probability which encodes the network confidence level, we need to quantify this into an actual predicted label of either good track or duplicate track. And for this, we use a decision prediction threshold such that if the output probability from the model is greater than the prediction threshold, then we're going to predict that this is a duplicate track. Otherwise, it's going to be a good track. One other way in which we can gauge the performance of our model is by using a confusion matrix. And then here it's shown on the right for the default prediction threshold of 50%. And what we can see is that our network is doing really good on the good tracks. It's getting almost all of them correctly, but it's not doing well on the duplicate tracks. And what this shows us is that we actually do need some extra information if we want to increase the performance of our network in this particular area. But considering the limitations of our input data set and how we currently cannot expand upon it yet, the network performance is actually adequate for the purposes of what will follow. Finally, we can look at what the network has actually learned about how to try to identify duplicate tracks. And again, we see that the network has learned the easy, accessible case, which is it can distinguish the duplicates that actually do look kind of funky in the sense that they have fewer hits, they have lots of outliers, and they have a large chi-square per degree of freedom. So this is easy for the network to identify. Where it's having issues and being confused is in the case of the duplicates that actually look like good tracks in this particular feature space. So the ones that have like a large number of hits, they have very few outliers, and they have a reasonable chi-square per degree of freedom. And certainly in this case, we're going to need extra information, such as, for example, information about the shared hits that these duplicates have. And this is likely to help us improve the performance of the network at this particular task. One other thing that I like to mention here is that currently we're using the network to make our predictions on a track-by-track basis. So we show it one track and ask it to predict whether it's a good track or a duplicate track. But a very interesting idea for some further exploration in the future would be to develop a network architecture in which the network can pick out the best track from a set of multiple track candidates. So now that we have our network and it's performing adequately considering the limitations in our training set, we can go ahead and try to implement the predictive functionality of our neural network back into ACTS, which was the second major part of the project. So we do this by using a C++ class, which we called ML track classifier. And in the version 1, our class consists of two important members. The first one is a vector, which we use to store the train weights matrices corresponding to our best neural network model and TensorFlow for each of the layers in our model architecture. And for this, we use dynamic size eigenmatrices to store our train weights and also take advantage of the linear algebra operations that these data structures support. The second important member is the function which does the prediction, the predict track label called in this case. And what it does is it essentially performs the linear algebra that describes the whole network. So for each of the layer, we had to code a function that can take the input, add the correct bias term, apply the correct weights for that particular layer, and at the end, apply the correct activation function for that particular layer, and then repeat this over and over until it describes the whole network. And finally, at the end, we implement the decision threshold, and based on this, we will predict a label of either good track or duplicate track. And in order to verify that our implementation is correct, what we can do is we can use this ML track classifier class and use it to generate duplication rate plots for a particular set of track candidates that we ask it to analyze. So if we do that, we can then compare, for example, the duplication rate versus eta produced by using our classifier implementation inside of ACTS, and this is the plot shown on the right. And compare this to the duplication rate versus eta plot used if we do the same thing directly in TensorFlow. So we use the same set of track candidates and we ask our model implemented in TensorFlow to predict which one of them are likely to be duplicates and then generate the duplication rate versus eta plot. And what we can see is that the two plots are identical to each other. And we've also found, although not shown here, that plots of the duplication rate versus the parameter phi or versus pt are also identical between the two versions, the C++ and the TensorFlow version. So this is a nice check that we didn't introduce any coding bugs in our implementation, and things are working as they should. However, as we were working on this implementation and talking amongst ourselves and with other people, we came to realize that this V1 implementation has several limitations. Namely, the fact that it currently implements one single network architecture, the one I showed a few slides ago, and this network architecture is trained on data that is generated from one particular detector plus magnetic field configuration. We also had to handle the linear algebra that describes the network's prediction function by ourselves. But what we would like to have is something that is a little bit more general in the sense that it's easy to switch between different detector plus field configurations without having to rewrite a major part of your code base. But also, it would be nice to have something that can be easily used as a framework for other machine learning-based tasks, not necessarily just track classification. So with these ideas in mind, we decided to look at the Open Neural Network, or ONNX for short, format and runtime. This was partially motivated by the fact that this format has already been integrated in Athena as a general framework for machine learning tasks for Atlas. So clearly it was, we decided it was worthwhile to explore ways in which we could implement this ONNX format and runtime for use with ACTS. A nice feature about this format is the fact that it supports many different machine learning frameworks. So in this sense, you're not forced to do your training in only one particular framework, and you could equally well use TensorFlow or PyTorch or scikit-learn or some other ML framework that you're comfortable with. And at the end, once you have your trained model, you can just use an appropriate conversion script, which the ONNX people provide. And then this will actually save all of the information about your model, such as its architecture, the train weights and train biases, as well as compiler information into the open source ONNX format. And then if you want to use this model to make some sort of prediction, then you can use the ONNX runtime inference accelerator, although even here you have the option of using other accelerators. And what is nice is the fact that the ONNX runtime in particular has APIs for several languages, of which, of course, the one relevant to ACTS is C++. But perhaps the biggest selling point for this is the fact that the runtime abstracts away all of the complex linear algebra that is associated with a machine learning model, and it just handles it behind the scenes. And this is something that the user doesn't have to actively handle by themselves. So the ONNX integration is currently a work in progress, and we hope to have this done soon. And in this particular implementation, the version 2.1, we're trying to rewrite the ML track classifier class as a wrapper around this ONNX runtime functionality. And again, because the runtime already handles all of the linear algebra behind the scenes, and that's something that we don't have to worry about. Now, our predict track label function, instead of having to do all of the linear algebra by itself, it essentially only has to implement the decision threshold step, in the sense that if the output from the model is greater than your threshold, then you would predict that the track is duplicate, otherwise it would be a good track. So that's the only thing that from the user perspective, the prediction function has to do. As a little technical aside, all of the information about the model is stored in this data structure, which is called the ONNX runtime session. And here it's just like you load all of the information about your model. And then you can actually do the inference step in the usual way of model.predict from TensorFlow, for example, which is quite nice. Because this means that the only thing that the user has to take care of is make sure that the runtime is pointing to the correct model file in the ONNX format, and also making sure that the input from the code they're writing is set up in the format that the model expects. And perhaps, depending on the machine learning problem that they're thinking about, they have to handle how the final decision is made. But that's it. And there's at no point in here does the user have to worry about the fact that they're implementing the correct algebra operations that they're described at their particular model, which is quite nice. And this certainly hints that it's easy to generalize this if you just have to change which model you're using and also the way in which the input is set up, but that's it. So to conclude, I like to say that to us, it seems that the ONNX runtime and format seem to be like a very good solution for a general purpose machine learning framework that can be used in ACTS for a variety of machine learning tasks. And certainly finishing up this implementation is our goal for the immediate future. But we also have several other future plans for the more distant future, centered particularly on trying to improve the network's performance at the ambiguity resolution tasks. Although, as I mentioned before, in this case, access to additional information about the duplicate tracks, such as the shared hits between the tracks, will certainly be needed and will help in this regard. And as one comment on a future plan, it would be very interesting to try to develop and train a more complex neural network architecture using data that comes from a more realistic description, detector description, of course, once that becomes available. So that was everything that I wanted to share with you today, and I would like to thank you for your attention.
Great, thanks a lot, Irina. Are there any questions? Sure, Gordon, why don't you go ahead?
Okay, can you hear me? I'm having some serious internet problems this morning.
Yeah, you're good.
Yeah, it's okay.
Okay, great. That was a fantastic talk, Irina. Thanks for doing it. I had two questions. one technical and one sort of both forward-looking. So one is the technical one was, I think the Onyx work is great. I especially like this idea of an adapter that frees us a little bit from which type of neural net training we use. Do you know if it's something that experiments and maybe particle physics is looking to there's a chance it will be adapted as opposed to us all having to implement every single different neural net back end? And then the other question I had was, looking towards the future, as the geometries get more complicated, is there evidence that this method will work better for classifying than our old the old methods that we've used? For simple geometries, we can use a simple network, but I sometimes get worried that for a real detector geometry with all its weirdnesses, that trying to train a network that can actually work well is going to take a huge amount of resources.
So for your first question, we're just have started looking into the runtime. So I'm not sure if this is the answer you're looking for, but as far as I can tell, the only thing that the user would have to do is, they provide conversion scripts, which are just little command line interfaces, which you can use to convert your model from a TensorFlow format to, for example, to the Onyx format. And in that case, there's you could presumably even write a script in whatever language you want that just handles this. So I'm not sure if that's the answer you were looking for.
Maybe, Irina, I can add something.
Sure.
That actually, Gordon, there are some folks on the Atlas side. In fact, it's a group of people from US Atlas who have been working on the implementation of Onyx in Athena. So that's actually where we got the idea to use it here. So I believe, at least for Atlas, it's something that we're planning to use.
Do you know if CMS is looking at the same sort of thing? I'm sort of hoping the field is eventually going to converge around one thing so we can stop having this sort of discussion.
CMS is using it.
They are.
Yeah.
Okay, great. Thanks, Irina.
Okay. And then for your second question, I'm having, I guess, the same question which many of you are probably having, which is, exactly how do you know when a network has learned the correct thing? Or rather, it's difficult to assess whether the network is learning the correct things or not. And I feel like this is something that people are just doing based on experience. You try something and you see if it's better or not, and then you try to go back and understand. But yeah, I'm not a huge expert in machine learning, so I'm not sure, but it certainly seems like there is some sort of subtlety between using a simple model in which something would be fine and then something more complex in which it would have to be some significant investment of time to try to make sure that it's working correctly.
Great. I mean, I guess the nice thing is that people have demonstrated over and over again that the models often do better than what we can write out procedurally. So there's good hope that it would be the case. But your comments, I've heard many people, and myself included, make comments similar to yours, and I've often referred to neural network design as one of the dark arts because I haven't figured out what the logic is yet. All right, fantastic. Thank you so much. It was a really good talk.
Thank you. And yeah, you're right. For me as well, it feels like neural networks are kind of a black box, which you give it some data and you hope it works. And when it works, it's great. And when it doesn't, it's why did it not work?
Maybe just to add a more general comment. So Gordon, this is actually a problem for ACTS in general, right? Because we're intending this to be a track reconstruction toolkit that can be used on many detectors. And it's not just ambiguity resolution, it's any other part of the tracking. There are actually a number of parameters that are important to tune. And actually, I'd say maybe the opposite to you. One of the things we've been thinking about recently is maybe you actually want to set up some sort of machine learning algorithm that could actually automatically tune track parameters, for various different detectors, because otherwise, if you're doing cuts by hand, you have to go and do it one by one for each of them. It's just a thought at the moment we've been thinking of.
Oh no, that is totally, I think totally the right direction to be thinking in, and thinking about that, but transplanting it to thinking about an analysis where, at the moment we just tune for a single benchmark sample, and then we happen to run on a bunch of other samples where you can make some variations to some of your basic cuts to really improve the optimization on different signal samples. And this is where the whole idea of this differential programming, I think one of the reasons that it popped up in particle physics is the idea that even when you just have regular parameters, not neural nets, you would like to apply some of the training, the training techniques that we currently use for machine learning, but to those other places. So yeah, I totally agree. I think it's the right way to think. I have no idea what the right answer is, because differential programming looks to me like, throw everything out and start from scratch again, kind of a situation, which there's no way we could do.
Any other questions? Okay, well, thank you, Irina. Let's switch to our second talk. So it's going to be Lucas. Lucas, can you share your screen?
I will, yes.
Great, why don't you go ahead?
Okay, yeah, hello everyone, I'm Lucas. Today I'm going to be presenting my GSOC project. I've been working on reducing boost dependency in CMSSW code base. So first, what's the idea of the project? The idea is that standard C++ introduced on recent years a lot of features that were only previously okay, let me start again. The idea of the project is to reduce CMSSW technical debt by finding and replacing boost dependencies that have an equivalent solution with standard C++. So in recent years, standard C++ introduced a lot of features that were only available through boost packages before. So the idea of the project was to find and replace these equivalent solutions. So the first stage of the project was to find and replace dependencies that had a very similar counterpart in standard C++. So just for example, boost array, right now in C++, we have std array. Another example, boost another map, we have std another map. So if we can find and replace those dependencies, we can upgrade our code and make it more standard. So just for example, boost bind, we can replace it with std bind very easily and without any costs. It's just like the cost for us to find and replace those dependencies. So for this, we've used automation tools like Tidy or SED to find and replace a lot of those dependencies. So this was the first stage of the project. On the second stage, we were trying to find things that could be replaced, boost dependencies that could be replaced using a minor workaround on C++. So in the second stage, we were trying to find things that we boost dependencies that we don't actually need because we can use a clean workaround in C++. So for an example, boost non-copyable. Boost non-copyable is a dependency of boost that makes a class to be non-copyable. So instead of using boost non-copyable, we can simply delete the copy constructor and the copy operation, and we can remove this boost dependency. So there was a lot of those type of dependencies. For example, boost PTR vector, boost matrix, boost MPL. Another example, code example, is boost MPL. We can replace, for example, boost MPL if with STD conditional or static contra expressions. So yeah, and these are the results of our work. We could replace a lot of dependencies that weren't needed anymore. We reduced 1,000, more or less 1,000 boost references in the CMSSW code base, and 400 boost includes, more or less. So these were the results of the first part of the project. I would like to mention that there are a lot of boost dependencies that are still in CMSSW code base that we can't replace because they don't have a clear replacement in standard C++. For example, boost algorithm, boost POSIX, boost rejects. This one doesn't have a clear replacement, and they are still in the CMSSW code base. I would also like to mention that some of those will still be able to replace in the coming years. For example, boost format, we probably will be able to replace for STD format in C++20. And yeah, so I would like to talk about boost modules, C++ modules. C++ modules are an upcoming feature that will be introduced in C++20, and it tries to replace this standard header model. So there are a lot of advantages over standard header model. For example, C++20 modules are much more scalable because you can compile them just once, and you don't have to compile for every translation unit like the standard C++ model. You also have a lot less naming collisions because they are isolated. For example, in standard C++ headers, you can have collisions with macros. So modules try to fix that. And overall, C++20 is going to try to move C++ to a more modular approach instead of a classical header textual include approach. So one thing that my project helps is because if you can reduce boost dependency, we can more easily introduce modules to the code base. So this was the last part of my project. During this last month, I was working on trying to make boost modules work. So we're trying to modularize boost. One thing that is important to notice is that one thing that modules have, one feature of modules is that they compile on their own. So that's why they are much more efficient than classical header. They compile on their own. So one thing that boost that we needed to do is to fix boost headers so they can compile on their own. And that was basically the work that I've been doing this past month, is trying to fix and update boost headers to make them compile on their own and meet the criteria that we need to use modules. So that's basically it. And the previous project of reducing boost dependencies was very useful because now we have much less boost headers to work on and fix. And the output of this phase, I'd like to mention that this was not just my work. I've been working on with Vasil and David. So we had we were able to build 85 Boost modules, and we were also able to update 57 patches to Boost. So these patches were actually merged with Boost. So yes, these were the results of this last month of work. And yeah, I think that's everything I have to say. If you want to have any questions, you can go ahead. Thank you.
Great, thanks, Lucas. Yeah, are there any questions? Maybe I'll start with one then. So I guess you're probably coming to the end of your project, but how would you see this moving forward? Do you think there are more that could actually be dealt with in the same manner, or do you think that already now you've kind of taken care of most of them?
Yeah, I think there are still some Boost modules that will be needed to work on. So I'm actually still finishing things, and I'll probably still work for some more weeks to try to finish the modules that we still haven't built.
Okay, thanks. Gordon, he has a question.
Yeah, thanks for the talk. It was really nice. I just a quick question on the modifying the Boost modules. I'm sorry, modifying the Boost source code to support C++ modules. Is that work the Boost collaboration or project or whatever is doing, or are you going to be able to feed that back to them? Because it seems like you know, that's something they would hopefully want if they don't have it on their roadmap.
Yeah, those 57 patches that I've mentioned were also merged on Boost. They are already on Boost developed branch. So
Fantastic.
we are actually trying to send PRs to Boost, and not just our
no,
local Boost.
I love the fact when, you know, in high energy physics we get to give back to the larger community. Like that is really great.
Mm.
Great. Any more questions? Okay. If not, then thanks again, Lucas, and thanks, Irina, and thanks for everybody who came by today.
Okay, thanks.
Yeah, thanks
Bye.
everyone. Thank you. Bye bye.